Hello everyone, welcome back. Let's look at chapter 8. So chapter 8 is about confidence intervals. So it's the first chapter that we start to discuss the inferential statistics. So for the first three chapters, we discussed about the descriptive statistics. We have the graphical way and we have the measurements. And then for chapter 5, 6, and 7, we discussed something about mathematical statistics. We have the probability, and then we have the discrete distribution, and then we just finished the continuous distribution. So starting this chapter, let's look at inferential statistics. And the first one we're going to discuss is these confidence intervals. So this chapter, we have two sections. We're going to discuss confidence intervals for population mean when the population standard deviation is known. In section 8.2, we're going to talk about what about the confidence for a population mean when the standard deviation is unknown. Or we say sigma known for section 8.1 or sigma unknown for section 8.2. So now let's see section 8.1, confidence intervals for a population mean, standard deviation known. So one aspect of inferential statistics is estimation, which is the process of estimating the value of a parameter from information obtained from a sample. So for this estimation, I think we discussed a little bit when we introduced inferential statistics. For example, if we want to know the average weight of SHSU students, then we have something called population mean, the average weight, which is the mu, population mean. Since census is almost impossible for over 21,000 students at SHSU, so what we want to do, we want to estimate. So this estimation is a process of estimating the population mean, mu. So what we're going to do, we draw a sample and then use the sample information to estimate the population information. And we say sample measures are used to estimate population measures, or we say statistics are used to estimate parameters. For example, a sample mean is used to estimate a population mean. So a sample proportion will be used to estimate a population proportion. And these statistics are called estimators. So we use X bar to estimate mu. A point estimate is a single number that is used to estimate the value of an unknown parameter. So for this unknown parameter mu, the one that we're going to use to estimate this mu will be the sample mean X bar. So we say X bar is a point estimate for the population mean mu. So we have three properties of a good estimator. We want it to be unbiased, consistent, and relatively efficient. Actually, we have a full chapter to discuss just the unbiased, consistent, and relatively efficient. But since we don't do any more math stat, so we'll just need to remember all those properties, and we don't prove for those. And an interval, now we gonna look at the interval estimate. An interval estimate of parameter is an interval or a range of values used to estimate the parameter. This estimate may or may not contain the value of the parameter being estimated. So interval estimate means we want to say we don't know the population mean mu, and then we want to say this mu is between a certain range. So maybe from some sample, we can calculate that the average weight for SHSU students will be 135 pounds to 165 pounds. So that's a range that we use to estimate this mu, and then we call that the interval estimate. And from that interval estimate, we're going to learn something called confidence interval. And then that's the main thing for this chapter. And before that, we're going to look at what is a confidence level. So the confidence level of interval estimate of a parameter is the probability that the interval estimate will contain the parameter, assuming that a large number of samples are selected and that the estimation process on the same parameter is repeated. And it's a percentage between 0% and 100%. So from the previous definition, we know that the interval estimate may or may not contain the value of the parameter being estimated. So since we give it interval, we don't know whether this mean mu is within the interval or not. But we can actually, based on the large number of repeats, and control that interval to have a probability to say that the true population parameter is covered. So we can say about 90% of those intervals repeatedly do the interval estimate. About 90% of the intervals covers the true mean, and then about 95% covers the true mean, and 99% cover the true mean. So that's what we call a confidence level. And a confidence interval is an interval that is used to estimate the value of a parameter involving the confidence level. So we call it confidence interval. So taking an interval estimate and take the confidence into consideration, we have a confidence interval. And now let's look at the example. So 26 confidence intervals of the mean price of all new mobile homes, each based on a sample of 36 new mobile homes. We have a total of that's 1 billion mobile homes in the US, and then we happen to know the true mean is 65. So this is by some research. The true mean mu equals 65. So usually we don't know this, but this is an example. We just pick up an example with the true mean known. Okay, and then let's look at sample 1. So we draw a bunch of numbers for this sample, and then we calculate the sample mean, and then we can for applying some formula, we can calculate this 95% confidence interval. So now we need to look at if this is a 95% confidence interval, what does this confidence level mean? From this example. So we draw a sample from this 1 billion mobile homes, a sample of size 36. So we draw first sample with 36 numbers from this 1 billion numbers. And then we calculate the mean, and then use some formula called the confidence interval. Then we can check whether the true mean mu is in the interval or not. So for this one, it happened to be in the interval. So we say yes. And then we draw a sample again, and then look at whether the mean is in the sample or not. And then we say yes, and then until we did all the 25 samples. And now for the sample 26, we draw 36 numbers again. We calculate the sample mean, so just add up all those together. So equals, and then sum over n, which is sum of all these numbers divided by 36. We got 64.8. So for the sample 26, we got x bar equals 64.68, and then the 95% confidence interval calculate by some formula to be 63.98 to 65.38, and then we look at whether mu is in this or not. It is in there, right? Because 65 is more than 63.98, smaller than 65.58. 0.38. So we say yes again. So 95, now we can look at this 95% confidence level means what? So if you repeatedly do this sampling process, you will see about 95% of those intervals covered the true mean. So now let's say if you have 100 intervals, and then 95% is about 5 intervals do not have the true mean. So right, 95, if you have 100 those confidence intervals, and then you should expect 95 covers the true mean and then 5 not. Now you have 25 about 1/4 of the 100 samples. Then you should expect 5 over 4, which is 1.25. That's about 1. Just round it to 1 no. So let's see whether we have 1 no. The no is right here. So you will see about 1 for only 25, around 25 samples. You repeat for the same process. Doesn't cover the true mean. So that's how we explain the confidence level. So it's still from the frequentist perspective, similar to we interpret the mean of a random variable. So now let's look at some concept about the interval. So now that we know what is the confidence level, then we say if we're looking at a 95%, 90%, 99% confidence interval, most of the time your CI, the confidence interval, is okay, because if you repeat this 100 times, only 1 time or 10 times or 5 times, this number does not cover the true mean. So it is okay. Then we're going to look at how to generate this interval by introducing margin of error. So margin of error, also called the maximum error of the estimate, is the maximum likely difference between the point estimate of a parameter and the actual value of the parameter. For example, we want to know the average age of all SHSU students, and then we say that's the true population mean mu. We cannot get that value because we cannot do census. So we obtain a sample and get an interval estimate, which is from a number to a value. It's a range. So we say mu is between 21.9 and 22.7. Then we rewrite this, because this actually generated by 22.3 plus 0.4 and 22.3 minus 0.4. So 22.3 plus 0.4 equals 22.7, and then 21.9 equals 22.3 minus 0.4. So that's how we actually get 21.9, 22.7. Then the equal difference we have here is 0.4 from the lower limit and the upper limit of the interval. And we say 0.4 is the margin of error. 0.4 is the margin of error. And then we're going to look at how to get these confidence intervals. We do have a formula to do that, right? So now let's look at the procedures to get a confidence interval. The assumptions for finding a confidence interval for a mean when sigma is known. We say the sample is a random sample. That's the first assumption we have. And either we have sample size more than or equals 30, or the population is a normally distributed population when we don't have that large of the sample size. And before we look at the procedure, another thing to know is the symbol Z sub something refers to Z-score with an area of alpha, or with a sub notation to its right. So for example, let's insert a new slide. So new slide is empty here. So if we say Z sub alpha, then we're looking at a Z-score in the standard normal distribution, that a number here, we call it Z sub alpha. That means number to the right, we have this alpha as the area or probability. So is a opposite of the percentile. So it's still a value or z-score in the standard normal distribution. Percentile that describe anything below, and this z-sub represent anything above. So it's just the opposite. And now that we look at z-sub alpha over 2, what does that mean? So that just means if in a standard normal distribution, a number to the right, you have alpha over 2. So this value is going to be z sub alpha over 2. Then based on the symmetry Z, you have another area which is below negative z sub alpha over 2. So this is still alpha over 2. So that will be very useful when we develop the confidence interval. So now we give it a name. This value z sub alpha over 2 is called a critical value, And alpha comes from the confidence level. So if you look at this, if we say we want 90% confident, we want 90% confident, that means the majority of the area we want it to be 90%. And then the rest will be 10% but equally distributed to the two tails. Then each one is 5%. And alpha is equal the 1 minus the confidence. So alpha over 2, which is to the right, to the left, only 5% for this example. So we say alpha equals 1 minus the confidence level. And of course, alpha is in between 0 and 1 because the probability never exists in 0 and 1. And for example, if a 95% confidence interval is to be found, we have the critical value equals z sub alpha over 2. So that's going to be, because 95% alpha going to be 1 minus 95%, which is 0.05. And then if alpha equals 0.05, then the z sub, oops. So we're going to do draw. All right, there we go. So z sub alpha over 2 equals z 0.05 divided by 2, which is z 0.025. So this is the critical value for this 95% confidence interval. So that tells us we have different critical values for different confidence. So if you have 90%, then this value is going to change. Because if you want an area, a number in a standard normal distribution, that to the right you have 2.5%, you can actually find this out from the standard normal table by just checking the probability, associated probability below. So to the right you have 2.5%, then to the left you have 97.5%. So check the value inside out with the probability number 0.975, you got this specific value, and that is the critical value. So why we need that critical value? Because that critical value makes the margin of error of the interval estimate. So step 1, we want to find the critical value, and then based on that critical value, we're going to make the margin of error. The margin of error equals the critical value times the standard error. So from previous chapter, we know this is called standard error. Standard error. Since we're drawing a sample, this is just the standard deviation of the sampling distribution of X bar. So this is actually come from the sampling distribution. So we have the standard error times the critical value, which makes a margin of error. And then the limit will be, or the range will be X bar minus the margin of error to x bar plus the margin of error, like we see here. Then we make a confidence interval with a certain confidence level. So let's look at an example. What we can do from a sample. Given the following data set, ages in years of 49 randomly selected. So we have 49 numbers, that's a sample. And we know that n, or sample size n, will be 49. So 49 random selected people in the civil and labor force. Then from study, we know the population variance is 9. So population variance, we write sigma squared equals 9. That tells us sigma equals square root of 9 equals 3. So that's another information we have here. And then the x bar, we can actually calculate x bar, but it's given already. So x bar equals 41.4694. We want to find a 95% confidence interval. So that means if we do this repeatedly for 100 times, we should expect 95 times of the confidence interval really cover the true mean. So then 95% confidence tells us alpha equals 1 minus 0.95 equals 0.05. And then that tells us z sub alpha over 2, the critical value equals z 0.05 divided by 2, that is z 0.025. So z 0.025 is a number in the standard normal distribution that to the right you have 2.5%. So this is z sub alpha over 2, which is z sub 0.025. And now, how can we find this value? That means to the right, to the left, you have 0.975. Then we're going to pull out the normal table. And find 0.975 inside out. 0.975, we have an exact number here. And we rate it out 1.96. So 1.96 will be this z sub 0.025. Then we can just write down the 95% confidence interval formula. So x bar plus or minus z sub alpha over 2 times sigma over square root of n. So that is the sample mean plus or minus the critical value times the standard error. So now we know everything, just plug in. X bar 41.4694 plus or minus the critical value, we got it, check the normal table, we got 1.96, and times sigma, which is 3 over square root of n, which is square root of 49. So that's 41.4694 plus or minus. Let's get the calculator ready. So we type in 1.96 times 3 divided by 7, square root of 49 is 7. So 0.84, so 0.84. That's the margin of error. Then plus the mean plus the margin of error will give us a upper limit of the range, and then the mean minus the margin of error, which is the lower limit of the range. So we got it as 41.4694 minus 0.84 to 41.4694 plus 0.84. So 41.4694 minus 0.84, that's 40.6294. And then 2 plus 42.3094. So we say the 95 let's use another color. The 95% call is from 6294 to 42.3094. Okay, these two here. That is the confidence interval. Or we say the real interpretation. Then we can rewrite this as an interpretation of the confidence interval. So we're going to say what? We are 95% confidence that the we're 95% confident that the true population mean mu is from 42.6294 to 42.3094. So this is the interpretation of the confidence interval. Then let's look at some key facts. Sample size and accuracy. For a fixed confidence level, that means if we remain this number and change, increasing the sample size. So when n get larger, so because n is in the denominator, so something divided by a larger number, and the whole thing will be smaller. So this part will getting smaller. This alpha unchanged, then the critical value unchanged. That leads to this whole part getting smaller. Then when you get a larger sample size, then that improves the accuracy because the margin of error getting smaller. Then your range will be smaller, narrower. Then that is improve the accuracy of the confidence interval. And confidence, let's look at confidence then. For confidence, for fixed sample size, that means the standard error will remain the same. So this part never changed. This part never changed. And then decreasing the confidence level decrease the margin of error. So if you're decreasing this confidence level, so let's see, if you draw a normal curve, then increasing alpha means you have a larger alpha over 2. So this value is going to move to the left. So that means, because the center will be 0, move to the left means getting smaller. So decreasing the confidence level, you actually improve the accuracy, but it's a trade. Whether you want it to be more confident or you want the confidence interval to be narrower. So this is for this one. In practice, another practice problem, a random sample of 130 human body temperatures were taken and found to have a mean of, as X bar, 98.25 degrees. We also know the population standard deviation is 0.73 degrees. Want to construct a 99% confidence interval for the average body temperature of a human. If going into the study, it was claimed that the average human body temperature was 98.6 degrees, what conclusions could we reach? So let's look at the solutions first. We got all information listed. We have n equals 130, x bar equals 98.25, sigma, which is the population standard deviation, equals 0.73. And then we want the 99% confidence interval. 99% confidence means alpha equals 1 minus 0.99, which is 0.01. And then alpha over 2, which is 0.01 divided by 2. So we got 0.005. And then z sub alpha over 2, which means z sub 0.005. Then that means, so we can draw this here. That means to the, so 0 is right here. And then you have a z 0.005. So to the right, you have 0.5% area. Then you're actually looking at a 99.5th percentile, 99.5.995 is the empty area. Then check the table, you got 2.575. And then again, put your sigma down, which is 0.73. And then we have the formula. The formula will never change. 98.25 plus or minus 2.575 times 0.73 divided by square root of n, which is 130. So you got the margin of error here, which is 0.165. So this number comes from 98.25 minus 0.165. And then this is 98.25 plus 0.165. Then this is the range, the confidence interval we have. And we say we're 99% confident that the true population mean mu is from 98.085 to 98.415. And if going into the study, it was claimed that the average human body temperature was 98.6. What conclusions can we reach? So 98.6 is outside this range we have. So we were already 99% confident that the true mean will be within this interval. So for this to be true, the probability which is very low. So we cannot support that. Support that claim. That's what we're gonna have. Then let's look at some commonly used z alpha over 2 value. So when we look at a 90% confidence level, then we have alpha over 2, which is 0.05. Then we check 0.95. We check 95%, 0.95. So where's 0.95? Right here, right? Between these two values. So we read 1.6 and 4. 5, right? Because in between 1.64 and 1.645, so we read it 1.645, and then we already checked 95, 1.96, and same thing for 99%. We check it, we got 2.575. So 99%, we got 0.99, which is right here. 2.3, 0.99. That's going to be 2.325, 2.325. Okay, I think we, yeah. Okay, this should be 0.995 because it's alpha over 2. So we go to 0.995. So 0.995 is right here. So that's actually in between 2.57 and 2.58. So we read it as 2.575. So these are the most commonly used z sub alpha over 2 values. Okay, then we're gonna start section 8.2 in the next video lecture. Thank you.